All right, in this video, we're going to be doing some autonomous differential equation examples. I'm going to be working through multivariable calculus homework 5.3. So the first one is consider the logistic differential equation. I'm going to just copy it. P prime equals 10 times P times 500 minus P. So what we know about this from last year is that, okay, this is a logistic curve. It has a carrying capacity of 500, and then what I told you recently is the general solution to this thing. So I'm just going to kind of write that off to the side, because I'll be needing to use this throughout number one. So the general solution to P prime is K times P times L minus P is going to be, okay, it's equal to, I've got it written over there, it's L divided by 1 plus C e to the negative LKT, where C is equal to L minus the initial population divided by the initial population. It's just what we know. And so we're just going to use that result. We're not going to go through and solve this using separation of variables and partial fractions and all that stuff every time. That's not the point here. Okay, so A, it says, okay, the initial population is P of 0 equals 50. Okay, so I know what the equation is going to be. This K is the same as that K, so that's going to be 10. L is the same as that L, so that's going to be 10 times 500 is 5,000. Okay, so I just need to figure out the C. So C equals L 500 minus P0 is 50 divided by P0 is 50. So I've got 450 divided by 50 is going to be 9. Okay. Now I'm going to just say, all right, the particular solution, that's what they asked for, is going to be P of T is equal to L 500 divided by 1 plus C e to the LK, negative LK, pardon me, T. And that's going to be our solution. And then in part B, they're going to ask me to do the exact same thing with P of 0 equals 600. Okay, so C is going to equal L minus P0 divided by P0. Okay, so that's going to be negative 1/6. Okay. And then I'm going to have my particular solution is population equals carrying capacity divided by 1 plus C e to the negative LKT. Well, that'll still be the same. Okay, and yeah, and you can see with the L minus P0 divided by P0, if the initial population is bigger than the carrying capacity, that's going to go negative, and then you can think about what that means in terms of the population. Either way, it's going to approach that 500 horizontal asymptote. It's just like, you know, is it approaching it from above or from below based on that minus or that plus. All right. Part C, find the equilibrium solutions. Okay, well, I'll copy it again. Okay, equilibrium solutions are just where P prime is constantly equal to 0. So that would be if P was 0 and if P was equal to 500. Okay. Those are going to be the equilibrium solutions. And then in D, it's asking, are they stable or unstable? Okay, well, I think maybe I'll make the diagram for this one because it's a good thing to do. But I can also say that, you know, based on your knowledge of the slope field of this thing, okay, if you think about, well, if P is negative, let's just talk about if P is negative, then P prime is also going to be negative because it'll be 10 times the negative number times a positive number. And so any place where P is negative, the slope is negative. And so you can kind of envision, all right, if that's the t-axis and that's the horizontal asymptote. Well, we know from the slope field that the curves will either S up towards that or kind of decay down towards that. But then I'm also proposing that these things have a negative slope. They got to go away from the t-axis. So this one's going to be unstable down here. So this will be unstable, and this will be stable. Okay. how we're going to do this, you know, on other ones is we're going to make a little diagram here. I think it's called phase diagram. And that's going to be, okay, well, the carrying capacity equilibrium, and then the zero equilibrium. And hold on, what am I thinking here? Oh yeah, just choose a number between 0 and 500, and I know that I'm going to get a positive slope because, you know, that'll be something between 0 and 500, like 100, positive. And so I'm going to be, let's see, I'll just go here. I like to put 2 arrows when it's between 2 values. And then when p is bigger than 500, I was already talking about this, when p goes bigger than 500, this will be positive, and that'll be negative, so I'll have a negative slope. The function will be decreasing. That's how we see it's stable. They're both approaching that. And then when p is negative, the slope is going to be negative for reasons I've already gone through, and that's why it's going to be unstable there. Let's solve for that one. The second one is consider the differential equation y prime is k minus y, where k is just a constant. Okay. This one's very frequent in AP Calculus. Find the general solution. So I'm just going to solve this one. I'm going to solve it by separation of variables. I'm going to divide by k minus y. So I'm going to have 1 over k minus y dy is equal to dt. And I'm going to anti-differentiate both sides. So I'll have the negative of the log of the absolute value of k minus y equaling t plus c. And I got the negative to appease the chain rule, right? Because I know that that's going to come out eventually, and so I got to prepare for that. Then I'll say that the log of the absolute value of k minus y is equal to negative t plus c. I will take e to both sides power. And then I'll say that's c e to the negative t. Okay, then I will, and now I'm going to get rid of the absolute value, and that will be plus or minus c e to the negative t, which, you know, if it was just going to be y is plus or minus c e to the negative t, then I wouldn't need the plus or minus, right, because that would be encapsulated in the constant of integration. But since I know I'm going to have to subtract that k and then multiply by negative 1, I'm going to need that plus minus. What am I thinking here? Oh, yeah, that's the general solution because they didn't give me an initial condition. That's what I was thinking. All right. The curve y of t equals k is an equilibrium solution. Is it stable or unstable? Okay, well, we can look at that. So I'm going to look at y being bigger than k and y being less than k. And I think, having worked this problem once before, I think the easiest way is to actually plug in k plus 1 and k minus 1. So if y equals k plus 1, then that's going to give me y prime equaling k minus y. So, and that's going to be a negative number, right? So it's going to be decreasing. And then, well, if you know there's first degree in y, then there's going to be a sign change, but you could also say y equals k minus 1. And that would give you that y prime equal to k minus, k minus 1. And that's going to be positive 1, which means the function will be increasing when y is less than k. And so I can see that it's going to be a stable equilibrium. Number 3, use the general solution to y prime equals k times y. Okay, I had some people asking me about this one. They were doing separation of variables repeatedly. That was not the point of this problem. Okay, so y prime equals k times y, we just know, because I showed you once, that this has solution y of t equals c e to the kt. That's the general solution. So when they say y prime equals 5y, with y of 0 equals 2, well, then I know what I'm really doing is saying, all right, well, y is equaling c e to the 5t, it's the number of y's, and I'm going to plug in 0 and 2, so 2 equals c times e to the 0, so that means to me that c needs to equal 2. And so my particular solution is y of t equals 2e to the 5t. And if you could just see that it was going to be 2e to the 5t from, from here, then you can just do that, right? Okay, the other two I've got, are a little, they have something else going on. So y prime equals negative 2y. And y of 1 equals 3. Okay. Nothing in here. Y1 equals 3. Oh, yeah. I know that y is going to be c e to the negative 2t. And yeah, I'm going to just plug in, all right. 3 equals c times e to the negative 2. And so I know that c is going to be 3 times e to the 2. So you can write y of t. You could write 3e to the 2 times e to the negative 2t, but I'm going to just combine those and make that 3e to the 2 minus 2t. Then that makes sense, right? When t is 1, I'm taking e to the 0, and I'm going to get 3. The third one. Y prime equals 3y with y of negative 2 equals 1. Okay, so I know the shape of it. It's going to be y equals c e to the 3t. And then I'm going to plug in 1 equals c e to the negative 6. Yeah. Then I'm going to multiply that over, and c is going to equal e to the 6. And so I know that, let's see, yeah, y of t is going to be e to the 6 plus 3t. Because, yeah, when t is negative 2, then I'm going to get z equal to 1. All right. And then the last one is, oh, yeah, the big polynomial in y. All right, y to the 5 plus y to the 4 minus 9y to the 3 minus 9y to the 2. Okay, you see this, you see 4 terms, you see the parallelism, it's going to be group and factor. And we're going to be able to factor this thing down quite a bit. So I'm left with y squared multiplied by y to the 3 plus y to the 2 minus 9y minus 9. And then I'm going to do group and factor on these. So I'm going to think about the first 2 terms, I can pull out a y squared. Then the second 2 terms, I can pull out a negative 9. And then from here, I'm going to factor out the y plus 1. And then I'm left with y squared minus 9, which I know that I can factor down into y plus 3 and y minus 3. Okay, so I've got it all the way down, and that will help me make a phase diagram. Okay, so I know that my equilibrium solutions are going to be 0, negative 1, negative 3, and positive 3. Pardon me. And so I'm just going to make a little phase diagram. And make sure to make it pretty long. All right, so the lowest one is negative 3. Then negative 1. Then 0, and then 3. Okay, and then I'm just going to pick a representative from each portion of the number line, kind of run it through the formula, and make my diagram and see if they're stable or unstable. Okay, yeah, I found the equilibrium solutions. That was part A. Now I'm going to determine if they're stable or unstable. Okay, so I'll start up here where y is big. So like maybe y equals 4. That's going to give me y prime equals, okay, well, y squared is always going to be positive. Y plus 1, well, all of these are going to be positive. Okay, so I'm going to be increasing from there. Between 0 and 3, that would be like y equals 1. And then that would give me y prime is a positive number times another positive number, and then a negative number when I subtracted 3, right? So this will be negative. So going down there, then when y is between 0 and negative 1, which would be like negative 0.5, then y prime would equal positive. Negative half plus 1 is also going to be positive. Negative half plus 3, positive, and negative half minus 3 is a negative number. And so we see the same behavior, like not a change in the positive negative, because of the double root there and that y equals 0. Something between negative 1 and negative 3. Okay, positive. When it's negative 2, that will be negative. Okay, negative 2 plus 3 is a positive number, and negative 2 minus 3 is a negative number. Okay, so all those together make a positive slope. Okay, and then y equals maybe negative 5, or you could do negative 10 or something. It was like way more negative. I'll do negative 20 or something. Okay, so that'll be positive, but then all of these will be negative. And then it'll be there. Okay, so I'm going to conclude that y equals 3 and y equals negative 3 are unstable. Okay, this one's going to be stable. This one will be semi-stable because over here it's going toward and over there it's away. And this one will be unstable. And yeah, I think that's all the problems we've got.